I wanted to take a chance and record a few more examples of proof by induction, just to emphasize what it means when I tell you that this is a formal proof, a formal exercise, and how that makes it different from a lot of the math that we've done. Usually, there's more than one way to find an answer, and yes, you need to show work, but the structure is unimportant. When you do proof by induction, the structure is absolutely a part of the proof. Now the structure remains the same. The specific words that you use can be different. I wanted to start by showing you an example from my math lab. So you're asked to use proof by induction to show that the given statement is true for all natural numbers n, and then it gives you your statement that you're going to prove. Your first step is to prove that this statement is true for all natural numbers n by showing that it's true for n equals 1. So no matter which words you use, there are going to be some words that fall down to we show that it's true for n equals 1, and then you show that that is true. You plug in 1, you show it's true. The next step is to assume that the statement holds for some value k, and then usually we write it out in terms of k, and determine whether it then holds for k plus 1. So that gets us to that third step where we solve using k plus 1. So we started with 6n minus 1, that becomes 6k minus 1. 6n minus 1 is equal to this. So 6k minus 1 is equal to k times 3k plus 2. And then if I substitute k plus 1 into this, there's my k plus 1, that's that next term, and I'm also going to substitute it in for k on the other side, so k plus 1, k plus 1. I've got to make sure I distribute, and then I've got to make sure that I multiply, and when I'm done, I'm going to show that both sides of my equation simplify to the same spot. Now that same spot needs to be whatever it needs to be, but it's going to simplify to the same statement. And then my math lab wraps that up with a final summary about why we have proven that it's true for any natural number n. So this is what it looks like with my math lab does it. I found this online and I really like it. I think it's very straightforward. 1, 2, 3. You're given S, some conjecture involving a positive integer n. We want to prove that S is true for all positive integers, and we can prove that if these three conditions hold. It holds that the statement is true for n equals 1. Then if it's true for n equals k, we can assume it's true for k plus 1. Alright, we're going to do a few of these. I'm going to show you what I mean by making sure that you use the words. Proof by induction, we're going to use induction to prove that this statement is true for every positive integer n. So here's our statement, S or S sub n. Again, there's a little difference in notation, but it does not affect the outcome or the structure. My first step is to show that if n equals 1, my statement is going to be true. So I'm going to take 1 and I'm going to plug it in. So I've got 12 is equal to 6 times 2, which is 12. So that is true for n equals 1. And then I'm going to say if my statement, S sub n in this case, is true for n equals k, and then it's a lot easier if you go ahead and write that down so that you know exactly what that looks like, because we're going to use it with our substitution here in a minute. So that becomes 12k equals 6k times k plus 1. So if my statement S sub n is true for n equals k, then that third step is to show that the statement is true for n equals k plus 1, that next term in the sequence. So I have all of this up to, let's see here, all of this up to 12k equal to 6k times k plus 1. So I'm going to do this substitution. I've got all of this represented by 6k times k plus 1. And then I do the next term. So I plug in k plus 1, so that's going to be plus 12 times k plus 1. And that's going to be equal to, and then over here, I'm replacing the k with k plus 1. So 6 times k plus 1 times k plus 1 plus 1. So wherever I had a k, I substituted in k plus 1. All right, now I've got some algebra to do. I need to show that these two statements reduce, simplify to the same spot. Let me switch colors. Over here, I've got 6k squared plus 6k. Then I distribute here, so I've got 12k and 12. And on the right side, I distribute here. That gives me 6k plus 6 times k plus 2. So on the left, combining like terms, 6k squared plus 18k plus 12. On the right, I'm going to FOIL. Well, 6k squared, my outside product is 12, my inside product is 6k, so that's 18k, and 6 times 2 is 12. And we have proven that it's true because it works for that next term, k plus 1. All right, so we're going to do a couple of others that look a little different. Let's do this one next. Now, remember, we're using words and structure. Now, the words and structure are important. The exact words are less important than the structure and the fact that you are using your words, that you're not just throwing some numbers down. Okay, so we've been given our statement S. N squared minus n plus 2 is divisible by 2. We are going to start with that first step. If n equals 1, then S is true. And we show that by plugging in 1. So 1 squared minus 1 plus 2. 1 minus 1 is 0, plus 2 is 2. So that's true if n is 1. And then my second step, if S is true for n equals k, and I'm going to show what that looks like. If S is true for n equals k, then, I'm sorry, I got switched on the wrong, I got distracted. I would have k squared minus k plus 2. Then, I want to show that S is true for that next term, n equals k plus 1. And so everywhere I have a k, I substitute in, let me get a little brighter color. That would be k plus 1 quantity squared minus k plus 1 plus 2, parentheses are important there. If I square this binomial, I think about foiling it out. I would have k squared plus 2k plus 1, and then I distribute that negative, so minus k minus 1 plus 2. Now I have all of these terms here, and I need to be creative and make sure that I can use what I know to show that this is still divisible by 2. Instead of just automatically combining things, I'm going to slow down and back up and say, okay, well, I know that these three terms, I've shown that these three terms are divisible by 2, so I can pull out those three terms. K squared minus k plus 2 has been shown to be divisible by 2, so we know that that is divisible by 2. And then what I have left, 2k plus 1 minus 1, well, plus 1 minus 1 is 0, so plus 2k, and 2k is divisible by 2 because it's multiplied times 2. So that checks, and we have proven that it's true. That's what those problems look like. I was going to walk through this next one. I think I'm just going to kind of show you a screenshot. The reason I picked this next one was because of that dividing by 6 step. I want to emphasize that if you have a denominator, you can always multiply everything times that denominator in order to cancel it out. So if I multiply in a 6 here, that cancels. If I multiply in a 6 here, I've got to distribute it. So that would multiply to each of those terms. I multiply it to 6 here, and that cancels out that denominator, just so you don't have to work with all of those denominators. So there is another example. If you need to pause the video and take a look at that so that you have it in a little more detail. Let me see. I think that there was one other problem that I was interested in doing with you. Oh yeah, so from the written practice assignment, I thought we would take a look at number 3. So let me grab, you know what? I didn't grab a piece of paper. Let me grab a piece of paper, a blank piece of paper, and we're going to take a look at number 3. Okay, so here's our statement S, and we want to first back to our example that we were doing. Where did that go? Back to that example. We're first going to show that S is true for n equals 1. So if these are just constants, I'm going to look right here. That would be 2 to the 1 minus 1 equals 2 to the 1 minus 1. Well, that's 2 to the 0, and anything to the 0 power is 1, and that's 2 minus 1, which is 1. So that is true for n equals 1. And then my next step is to assume S is true for n equals k, and you'll notice that I've changed my wording just a little bit as we work through this. That's fair. If n equals k, then I have 1 plus 2 squared, all the way to that 2 to the k minus 1, and that would be equal to 2 to the k minus 1. Then I'm going to show that it's true for that next term, n equals k plus 1. Well, now what is that going to look like? For that one, we are going to take all of this and substitute it in for k, as 2 to the k minus 1. So all of this becomes 2 to the k minus 1. And then the next term is going to be k plus 1 minus 1. So plus k plus 1, where I had the k, I substituted in k plus 1, and then minus 1 is going to be equal to 2 to the k plus 1 minus 1. All right, so over here on the left, I've got I got distracted. Oh my goodness. Okay, I messed up my substitution. You guys hopefully caught that and were yelling at me and I couldn't hear you. Let's fix my substitution. So my substitution was that everything to this point is substituted as 2 to the k and then minus 1. And I was talking and writing at the same time and got lost. 2 to the k and then minus 1. So that's all of these terms. And then the next term would be to take that k and plug in k plus 1 for it, because that's the next term. And then this right side becomes 2 to the k plus 1 minus 1. All right, so everybody pause the show. Make sure you got everything corrected like it should be. All right, so let's clean up this left. We've got 2 to the k minus 1, and then this becomes 2 to the k again, so plus 2 to the k. So I've got right here, these are the same, right? So I've got 2 to the k's. So I had 2 to the k and 2 to the k, so that's 2 of those 2 to the k's. All right, next step. Well, this 2 is the same thing as 2 to the first power. And if I'm multiplying the base, my rules say that I add the exponents. So this could be rewritten as 2 to the k plus 1. Multiplying the base, add the exponents. Now both sides match, and so I have proven it to be true using proof by induction. Okay, hopefully this helps. The structure is very important. You are doing those same steps no matter which specific words you use. Words are important. Use words. They should follow this pattern, follow this pattern. Obviously, my math lab is a little more formal, uses more words than what I'm asking you to do here, but the words and the structure are all a part of the proof.